complexification of real vector space. Complexification. So in particular, one of the things that allowed us to do was to take a linear transformation from B to B, real, and define a complexified transformation, T sub C, from the complexified B to the complexified B. Now, we also had a theorem I proved for you guys, was that if beta is basis for B, then that implies that beta is, well, let's say here, let me try to be careful. So suppose beta is B1, and then we proved that, let's say beta tilde, which I usually would just call beta, but it would be B1 comma 0, the n comma 0, just be careful, is a basis for B sub C, which remember was the Cartesian product of B with B paired with a complex scalar multiplication. And so, an immediate corollary of this is that if you looked at, such a transformation T versus its complexified one, T sub C. Now T sub C basically is just defined by this. T sub C, let's see, in the parentheses notation, T sub C of x comma y is equal to, let's see, what is it? It's just T of x comma T of y. Now, last time I wrote that in the equivalent and more convenient way of writing it, which was that T sub C of x plus iy is equal to T of x plus I T of y. Those are equivalent notations to the same concept. So anyway, this complexified version of linear transformation is defined uniquely from the given real transformation. You can do that. And you can also compare, given this basis theorem we proved last time, you can compare the matrix. You can compare the matrix of T with respect to beta, and you'll see that that's actually the same as the matrix of the complexification of T with respect to beta tilde, beta tilde. Just to be pedantic here for a minute. Okay, so our main application that we're interested in of this whole idea is something like T of a linear transformation from, say, Rn to Rn, right? I mean, you could do Rm to Rn, but I'm most interested in the square case at the moment. Then this gives you the complexified T going from Cn to Cn, right? And and in fact, you could just erase the little. I mean, in practice, what people do is they don't even do this. They don't even say T sub C. They'll just say T like this, and they'll just say something in parentheses like extending the domain of T complex arguments. Sorry.
Wouldn't it be faster to just write the C though? Wouldn't it be faster to just write the C though?
Well, yeah, but usually when people write this, they don't write any of this. So, anyway, yes, that's true. Okay, so in particular, you could look at the problem of complex eigenvectors. So an example. Let's consider A equals to A, B, C, D, for which the determinant A minus lambda I works out to lambda minus alpha quantity squared plus beta squared. So previously, we would have said, we'd say what? Oh, no eigenvalue exists, right? in the reals, because why? If you have the characteristic polynomial is this, right? If p of lambda is equal to lambda minus alpha squared plus beta squared for some alpha and beta in the reals, then what we have is that p of lambda is equal to 0 for what? For lambda equals to alpha plus or minus I beta, right? Which of course, if beta is none, and you know, just to be clear here, this alpha and beta I'm talking about, these here, alpha and beta are real numbers, beta not equal to 0. Now, if beta is equal to 0, we'd have a real eigenvalue, right? It'd just be alpha, it'd be squared. If you have an algebraic multiplicity, you do. If beta is not 0, complex, right? Complex solutions. So in our previous discussion of eigenvector, eigenvalue problem, we just simply said, well, oh well, no real eigenvalues, no real eigenvectors, right? But now that we have this idea about complexification, we can consider A to say be the matrix. So let's kind of take a step back. You can talk about linear transformation T, right? So consider T equal to L sub A, right? To start with, we could think about it going from R2 to R2, right? But we can consider its complexification, right? Extending the variable to be complex, we have T, and by the way, the matrix is the same, right? So it's still T is equal to L sub A, even though I'm extending to the complex 2 space. The matrix doesn't change by the theorem we just proved. And so I can ask the question, are there any complex eigenvalues? And are there any complex eigenvectors for A, right? And the answer to that question is, well, yeah. There is a complex eigenvalue for A. Well, how do you define complex eigenvalues and complex eigenvectors? Same way we did before, it's just that you do what now? You allow the eigenvalue to be imaginary, right? You have an imaginary component. So the fact that the determinant of A minus lambda I is equal to 0 for lambda equals to alpha plus or minus I beta shows there exists complex eigenvectors, right? In fact, there have to be at least 2 of them. One for the eigenvalue, one for its conjugate. Alpha plus I beta and alpha minus I beta, right? Let's look at alpha plus I beta. Let's think about it conceptually here. So let's find the eigenvector U. Well, I'm sorry, I'm using the vector sign here. I hope you can forgive me. An element of C2 such that what? We have A minus what? Minus alpha plus I beta, parentheses, in any matrix, times U is equal to what? Well, that's equal to 0, right? Now, that's not entirely productive for what I'm after here today. In order to really see this, I need to write the complex vector as the sum of a real and imaginary component. So the typical notation that's used in this kind of context is something like this: U equals to A plus IB, where A vector and B vector are 2 vectors. They're in R2. Right. So then you can multiply out this equation here. You have A minus alpha plus I beta parentheses data A matrix times, let's see here, A plus IB vector equals to 0. And all I'm going to do now is just multiply that out. All right, I'm going to multiply that out. What I'm trying to do, guys, I know I can't diagonalize A, right? The matrix A, I know I can't diagonalize it over the reals because we don't have an eigenbasis, right? We don't even have one eigenvector in the reals. But maybe from this one complex eigenvector, I can find something, I can find some real basis, right, which reveals a simpler form for the matrix A in general. So my natural suspicion is that it somehow must have something to do with the real vectors which are sitting inside this complex eigenvector, right? Just like we had success yesterday, not yesterday, the other day, by looking at the real and imaginary components of the solution to the differential equation. Those were separately real and real solutions. So I kind of have a suspicion that the real and imaginary components of the complex eigenvector also must have some significance to the problem. Let's see what the significance is. Okay, stick with me here. So multiply this out, what do you get? AA. Let's see here. Any other real terms? How about I times I gives me minus beta B, right? Then what? Are there any other real terms? Oh yeah, minus alpha A, right? Any other real terms here?
Wouldn't it be plus beta B because you have a minus?
Thank you. Yeah, I got plus, minus plus, so it's I squared, but minus I squared is 1. Very good, thanks. And let's see, imaginary terms, I've got what? Oh, minus I beta A minus I alpha B, right? Oh, and then I've also got plus what? Plus I A B. Sorry, this is not the best way to do this calculation. This would have gone much nicer for us if I had instead looked at AU equals to lambda U. That actually makes the calculation a lot nicer. Sorry, we're this far into it. We're going to stick with it. Retrospect. Oh well. Now, so group everything together. You've got AA plus I times AB is equal to what? On the other side, if you put everything on the other side, on the other side I have what? I have alpha A, right? Minus beta B plus I, parentheses, beta A, minus alpha B, right? So this is a complex equation. I've written it in terms of real objects though, right? So you can equate the real part of both sides and the imaginary both sides. You get two separate vector equations here. And the two vector equations we get are really nice. The one equation I get is A times A, right, is equal to what? It's equal to alpha A times A is equal to alpha A minus beta B. But I also get that A times B is equal to what? It's equal to beta A minus alpha B.
I think it should be plus alpha B.
Have I done that?
Yeah, minus over it and then moved it together.
Yes. So what? Well, here's the thing. So let gamma equal to, let's say, A comma B be a basis for R2, then the matrix of P with respect to gamma gamma, in other words, the matrix of the linear transformation induced by A with respect to gamma gamma is just what? see up here? What is, I mean, so the matrix is what it's what we do, what we do, T of A, gamma, T of B, gamma. No, remember that T here is just equal to what? I mean, T is L of A, okay? So what's T of A? It's so this is alpha A minus beta B with respect to the gamma, and then beta A plus alpha B coordinate vector with respect to gamma. But if gamma is the basis A comma B, what's this?
Alpha minus beta.
Right? And the next one is beta alpha. So this gets us, I mean, basically I've proved a little theorem. If A is an element of R2 by 2, and lambda is equal to alpha plus I beta is an eigenvalue, beta not equal to 0, alpha and element reals, right? With eigenvector u equal to A plus IB. Of course, I mean complex eigenvector, obviously, right? Complex eigenvector. Again, that's a slight abuse of language. Technically, it's not really an eigenvector for A. It's an eigenvector for the complexification of A, right? So with complex eigenvector u equals A plus IB, then if we set beta, the matrix beta, equal to A concatenated with B, yields beta inverse A beta equal to alpha minus beta, beta alpha. And that's the next best thing to a diagonal matrix for the case that you have a complex eigenvalue for a 2 by 2 matrix. Now, what is that? What is that kind of matrix? I argue that you can pretty easily prove that that kind of matrix is a dilation times a rotation. So how to see that? How to see that that kind of matrix is a dilation times a rotation? Well, basically, just factor out the determinant. Notice that this is alpha squared plus beta squared, which by the way is non-zero, right? Times 1 over, well, fine. Writing. Alpha over alpha squared plus beta squared. Beta over alpha squared plus beta squared. Minus beta over alpha squared plus beta squared. Alpha over alpha squared plus beta squared. And I would argue that you can see that the determinant of this matrix, you call this thing R, you can see that the determinant of R is in fact equal to 1. Because when you calculate the determinant, you get this times this, minus that times that, but the minus gives you plus. You end up with alpha squared plus beta squared over alpha squared plus beta squared. So the determinant's 1. And also you can check, and I won't do this, but you can check that R transpose times R is equal to I. So this makes this an orthogonal transformation to determine 1. In other words, it's a rotation. You can choose cosine and sine to match those fractions. And then out front, you just got multiplication by some real thing. That's a dilation. So Questions? So I did it for an arbitrary matrix, but you can just do the same. The problem in your homework, right? In the problem in the homework, you've got numbers for these little, A, B, C, D. But all you got to do is find the complex eigenvector, take its real and imaginary, components, and you can use those as a basis to do the similarity transformation that will give you this. All right, so at this point, I'm going to go back and talk to you guys more about projections and some of the things that I haven't talked about yet about geometry. I'll cover as much as I can today. I'm pretty sure it's going to take me another full day on this. So for the next about 90 minutes or so, I'll talk to you about projections and how to calculate them. And then once that's done, then we'll go back to chapter 6.
You're not holding us
Good.
I'm holding.
So,
Wait, Dr.
yes.
What do you mean by go back to chapter 6?
Well, this is, I don't know.
Like chapter 6 in the book or the
Yeah, chapter 6 in the book. In the book. In my notes, goodness, we're all over the place in my notes. This is over in chapter 11 in my notes. Like, I took a different logical path previous times I've taught, so like, I am
All over the place.
abstaining from saying certain things about things beyond eigenvectors until we're done talking about everything there is to say about eigenvectors. So that's forbidding me to say certain things which are in the middle of my chapter 11. But anyway, let me stop talking about what I'm not doing and start talking about what I'm doing. So, all right, so back to projections. So, we had, so ultimately our goal here is to understand projection and orthogonal complements. Actually, that's not our ultimate goal. Our ultimate goal in this discussion is to understand what's called the spectral theorem. Okay? The spectral theorem basically tells us that for a certain kind of linear transformation, you get an eigenbasis. Not just an eigenbasis, though. You get an orthonormal eigenbasis. That's pretty awesome. That's like really special. But to get to there, we need a little bit more about orthogonal complements, and then we'll come back and actually use some complex arguments to finish the spectral theorem. So it's kind of, we need both ideas. That's why they don't talk about it until after I talk about complex stuff. Okay, so getting to the point. Suppose you have an orthonormal basis. Suppose Rn as orthonormal basis beta equal to, let's say, V1, Bn. Then x in Rn as x equal to x v1, 1. So the notation I'm going to use today, guys, following the book, is instead of saying dot product, I'm going to say inner product.
If you're still talking about.
Now here, yeah, at the moment, x comma y, x inner product y is equal to x dot y for us here. But, yes, I'm telling you the proof for Rn. And yes, the inner product here is the dot product. But the argument I'm showing you, most of the arguments I'm showing you today, can easily be generalized to an inner product space. And well, what's an inner product space? An inner product space is just an abstract vector space with some function like this that goes from V cross V to the reals with a couple of axioms. Axiom 1, you have ax plus y z equals to a x z plus yz. Axiom 2, symmetric. Axiom 3, the inner product of x and x is greater than or equal to 0, and the inner product of x and x is equal to 0 if and only if x is equal to 0. So these together make V paired with an inner product space. Now, an inner product space, Rn is an inner product space. You can also give inner products to like the matrices, square matrices have an inner product. You can find inner products for functions. You can find inner products for all kinds of stuff. And most of the arguments I'm going to show you about projections just as well apply to inner product spaces. In fact, that's when some of the more interesting applications come from. This thing I'm telling you about, plus some analysis that we won't get into, give you, for example, the Fourier decomposition of a function into its modes with respect to sine and cosine. Those form in some sort of orthonormal basis in a function space.
Should
Anyway.
both of those be V's and then we have x1, b1, where x equals right there?
No, this is right.
Okay.
So it's like V1. So I could write this like less clumsily like this. This is sum j equals 1 to n of x comma vj, like that. So how do you
And I was about to say, you never taught today. Have you gotten better? But now you're
It's all your fault. You made it
it's
wrong.
all Kristen's fault. It's here.
I didn't jinx it yet. You
Well.
caught him before I could jinx it.
You were
So.
thinking
Let
it.
x equal the sum j equals 1 to n of c sub j v sub j. Now why can I do that?
Because basis, beta is a basis.
As beta is a basis, that's right. And then what do you do?
Is C some constant?
Yes. Yes.
What are we proving here?
Then x has this.
But-
And if you would like me to replace it, I could say x can be written as follows.
But what are the conditions and what's the conclusion? So one
The condition is that x is a real vector in Rn. The conclusion is that I can expand its components in terms of the inner product of x with an orthonormal basis.
So
Okay.
if the first line, then everything else.
Mhm. Okay.
Cool. So let's see here. What's the inner product of x with, let's say, vi? Well, but by linearity of the inner product, right? Dot product, if you like. I can pull the sum out, and I can pull the scalars out by, okay, and additivity. And then what do I have? I've got v, vj, vi, dot product. Well, what's the dot product of vj and vi? If they're orthonormal, I mean, to say it's an orthonormal basis, a simple formula for that is just to say that vi dot vj, which by now is vi comma vj, that's just the product of delta ij, right? So in other words, this thing is either 0 if j is not equal to I, or it's 1 if j is equal to I, right? So all that remains then is what? C what?
CI.
Yeah, CI. CI is the J is the dummy index of summation here. I is a naked index. It's sitting over here. It's got to be in the final formula. So CI. But that's exactly what we set out to prove, right? Thus, x is equal to a sum. If you like, I equals 1 to n. X vi. You're like, but you said with j. Fine. If you insist on me writing it with j, I can write it with j at the end. But I mean, it's the same. Okay. You guys with me? What does this mean? This means that the coordinates with respect to an orthonormal basis are really, really easy to find. If I want to find the coordinate vector with respect to an orthonormal basis, all I got to do is take dot products with the basis, and that reveals the components. Of course, if you think about calculus 3 or physics, this is familiar. Because if I want the x component, I take the dot product with I. If I want the y component, I take the dot product with j or with y hat if you've had my classes, right? If you want the z component, take the dot product with z hat or k if you so prefer.
Is Cj equal to Ci because it's a constant as you count as your summation?
I'm sorry?
You have to assume that j equals I for it to be non-zero. Right, that to be non-zero.
It's all about that being 0 for everything except for the ith one. Only for I is that non-zero, and it's 1. So it's like 0 plus 0 plus 0 plus ci plus 0 plus 0 plus 0 plus 0, so it's just ci. Okay, so I'll talk to you about Graham-Schmidt. How do you do Graham-Schmidt? The Graham-Schmidt algorithm. So here's the input. 1, suppose we have S, let's say a linearly independent set. And suppose it's like V1, VK. All right. Step number 2, so you're given this. You're given this linearly independent set, subset of R or N, okay? So number 1, you let U1 equal to 1 over the length of V1 times V1. If you forgot, the length of V1 is the square root of V1, V1. So that's how to define the length. So there's your first one. Step 3, you let U2 tilde, what you're going to do is you're going to take V2 minus V2 dot U1 times U1. All right. That gives you a vector which is orthogonal to U1. But it's not necessarily normal. I mean, it might have length 2 or something. So you normalize this. So part of step 3 is then set U2 equal to 1 over the length of U2 tilde. So that makes U2 tilde into its unit vector, U2. Step 4, well, U3 tilde. What you do is you say V3 minus V3 dot U1 minus V3. Oh man, I'm using dot products again. Curses. V3 old habits.
That's right.
You can leave it. It's fine. It's not. I mean, I said they're the same, so whatever.
I guess teaching practice.
I mean, I don't get fired and stuff, I'm sure.
Why-
For no?
That's such a weird thing to bring up in casual conversation during class.
You never get out either.
It happens. Okay.
Is that what I brought up?
Not very well. It's out of the way.
I hope they don't fire you.
Why was it on
I'm
your
looking for
mind?
a complex.
You should just get tenure.
Why am I pushing it? Oh my gosh, what a jerk. Dr. Cook, I love you. I don't want to see you leave.
You should have brought flowers then.
And so forth. Eventually, you get to the kth one, and UK tilde you build from taking VK, and you subtract off like VK, U1, U1, and so forth and so on until you get all the way down to subtracting off the K minus 1th component. All right. This provides, the result of this is that you get this set, U1, UK, and the span of this will be equal to the span of your original set S. And you also have this lovely thing that UI, UJ is product or delta ij. In other words, it produces for you an orthonormal set. And you can do this for any linearly independent set. It's a completely general algorithm for Rn. Yeah.
For point 3, you have parentheses around v2 dot v1. Oh, because it's the same thing, because it's the end product. Never mind. I got it now.
Yeah, so let me show you one of these. You're like, numbers? You're actually going to do something with numbers? Yes, I will do something with numbers. Fine. Push you to it. You're happy. Suppose S is equal to 1, 1, 1.
Oh, that doesn't look like a problem. That's going to equal 42.
2, 2, 2, 0. I think that's linearly independent set. All right. I'm going to call this one V1. I'm going to call that one V2. So step 1, U1. 1 over the square root of 3. 1, 1, 1. There we go. There's your first normalized vector. And then I'll calculate myself a U2 tilde. What do I got here? U2 tilde. So I'm supposed to take V2 minus what? Well, I'm not going to write these symbology down. I have it right over here. Just go ahead and write it down. So what I do is I take 2, 2, 0, right? And I subtract, let's see here. See, I get a 1/3, 1/3, 2, 2, 2, 0, dotted with 1, 1, 1, times 1, 1, 1 is the vector, okay. So what's this dot product work out to? 2 plus 2 plus 0, 4. So I get 2, 2, 0 minus 4/3, 1, 1, 1, which by the way gives me 6 minus 4, 2/3, 2/3 minus 4/3. Here's a fun fact for you. If you factor out a number if you can, when you factor out a number, if you think about if there's a scalar, when you're normalizing a vector, the scalar is irrelevant. So you might as well throw it away. That 2/3 is going to be, up here, right? And the 2/3 is also going to be present in the formula for the length. So I can ignore the 2/3 as I normalize U2 tilde. So U2 is just 1 over the square root of 1 plus 1 plus 4, 6. 1, 1 minus 2. Yeah, sure.
Does this give us like a geometric mapping, or is this part of the spectral theorem?
We'll talk about the geometry of it pretty soon. It will provide us the projection, in fact, yeah.
So we just basically, I mean, we just like,
I'm getting there.
uh,
I haven't gotten there yet. Right now I'm just showing you this this cold algebraic algorithm, devoid of geometric anything. I mean, I just tell you that's how to do it. I mean, I do think, placed on a desert island, time on your hands, enough paper, pencil, pen, whatever, I think anybody can come up with this. This is not complicated, actually, what's going on here. Because all you're doing, like I said the other day, is you're just subtracting off the piece to create U2 tilde. What you're doing is you're subtracting off the piece of V2, which is in the U1 direction. See, this dot product, what that does actually is it gives you the length of V2 in the U1 direction. And so I'm just subtracting off the piece of V2, which is in the U1 direction, which only leaves me stuff that's not in the U1 direction, which must be orthogonal then. And then you just keep doing that.
Why don't I just tell all the Cat 3 students your secrets and this class?
Oh, this is all in my Cut 3 notes, yeah.
Like, I mean,
Yeah, but people don't understand.
well, the formula is completely different though, like, thinking them up, going like this, whatever, I'm making things complicated, whatever.
Yes, linear should be a prerequisite for every other math course, that's true.
Wait, so what did you do to like from there to there at the bottom line? Like the
I
arrow?
normalized it. So I did this. Okay, so you guys, back on track here. So what I have then is that the basis beta equal to, let's see here, 1 over the square root of 3, 1, 1, 1, comma, 1 over the square root of 6, 1, 1 minus 2 is an orthonormal basis for the subspace W, which I can define by the span. Let's say it's the span of S, all right? Now, suppose then I want to extend this basis for W to a basis for all of R3. How would you do it?
Take cross products.
We don't know cross products.
What do we do? The vector don't work. So
Okay.
we go.
Suppose that's
True,
true.
we've all taken calculus 3, so we did.
False.
Darn it!
To extend
Except this guy.
beta gamma equal to U1, U2, comma U3, an orthonormal basis. Orthonormal basis for 3. So you guys just thought of the third option. So here are my 3 options. Here are the 3 things I could think of to do it. Number 1, pick a vector, any vector. Pick a vector outside W. And then run Gram-Schmidt on it. Gram-Schmidt, usually call it Gram-Schmidt algorithm. I get sick of writing that, and I usually misspell it about half the time I say it, so let's just call it the GSA. It's certainly more useful than most of the things that bear the letters GSA. So, is there something here that's called GSA?
I'm failing to recognize the GSA.
Graduates.
For example, it's more useful than the Graduate Student Association. There's one. There's got to be something in the government that bears these letters. I'm sure it's more useful than that. Anyway, so that would be one. I did that. For example, if you pick, say, V3 equals to 1 minus 1, 0. All right, that's not in, there's no way you can get that from the span of these 2 things, right? And I just eyeballed it. I mean, you know, that's the, how do you take a vector outside a span? You guess. I mean, it's not, yes.
Well, I was going to say find a linearly one that's not dependent.
Exactly, but how do you actually do that?
Yes.
It's not when an equation is satisfied, it's when the equation is not satisfied,
You
right?
just write it as, you just guess until you find one that doesn't become.
That was my method. Now, But here's the thing, my guess is very fortuitous because if you look at this dot with that, 0. This dot with that. Oh, my guess is very fortunate.
Oh, I see.
Wait, so it has to.
So basically my gamma would be beta union with, I want orthonormal, so what do I have to do? My guess isn't quite ready. Normalize it, 1 over square root 2. 1 minus 1, 0. And there you go, that would be an orthonormal basis for R3. So you guys told me your method was to set V3 equal to U1 cross U2. Now, your method of using the cross product, not one I would usually advocate in linear algebra, because for some reason we don't know about cross product in linear algebra, as is our custom. Maybe it's a bad custom. That is in some sense superior because it's automatically length 1, because you're taking the cross product of two orthonormal vectors. And so the angle between them is 90 degrees. Magnitude of each one of them is 1. So that actually is, that will either give you plus or minus this. I'm not going to work it out. But that's kind of a drag to calculate the cross product, right? 3, and I like 3. 3 is a method I sometimes forget about. But 3 is to calculate W perp. W perp is the null space of 1, 1, 1, 2, 2, 0, which is the same as the null space of 1, 1, 0, 0, 0, 1. Why? Well, you do the row reduction, right? So you subtract 2 copies of the first one from the second one, and then flip the rows, you'll get to this. Maybe multiply by 1 or something. Anyway, so you can see that if ABC is in the null space, if it's in the perp, then what? Or maybe I should use X, Y, Z. Fine. What do you got? You got X plus Y equal to 0. You got Z equals to 0. So what do you got? You got yourself a 1 minus 1, 0. Span of that is W perp. Now, that's another way you could attack it. You can just find a basis for the perp. If it's one-dimensional, then you know that you're going to find the vector you're looking for. Sometimes that's easier. This gets more and more awful as the further you go. And and then just one last thing I should define for you guys today is the projection. All right, so what is the projection? So definition, W a subspace of Rn, and beta equal to V1, V2, da da da, Vk, a orthonormal basis. Orthonormal basis for W, we define the projection onto W of X is equal to simply the sum I equals 1 to K of, well, we do X comma Vi di. And then we'll also define the orth. The orth W of X is X minus the projection W of X. Let me just leave you with this geometric picture of what we did today. So this W we've been discussing is a subspace, right? In particular, it's a plane in R3. So if I am to picture it, this is W perp, it's a normal line. this is W. And what I've done is I've found a basis for, and we can easily use that basis to actually, so, to apply it to the example we've been working on today, just to complete the thought, this would be something like, the vector x inner product with like 1/3, 1 over square root of 3, 1, 1, 1, and then 1 over square root of 3, 1, 1, 1, etc. The other term. And this one ends up just being, as it turns out, this actually ends up just being x, comma, 1 over square root of 2. And this is not, maybe this isn't obvious yet, but it's 1. 1 minus 1, 0. 1 over square root of 2, 1 minus 1, 0. So what's going on is we have an arbitrary vector x out here. And what I'm saying is there's a shadow of that vector onto the W plane, right? And that's what we call the projection Wx. That shadow can be decomposed into two pieces. All right, and those two pieces look something like this, or like that. In particular, these two pieces are nothing more than like x, u2, u2, and then the other one is x, u1, u1. This other vertical piece actually forms the orthogonal projection, the piece which is not in the W plane, and that's exactly the third thing. That's x, u3, u3. Or you could, this is the orthogonal projection of x. With all of this in mind, I will be able to prove next time the theorem that W direct sum W perp is equal to Rn. And we'll be able to prove that without much difficulty. And once we know that, that is a critical part in proving the spectral theorem, which is what we're really after, which is really interesting for applications. So, anyway, I shut up. Have a good weekend. No secret CFARs here?
Told you, I'm safe.
Sorry, Landon, I couldn't hear you.
It's okay.
Wait, no, never mind.